I have a handout. Here's the thing. This handout is trivial. It's almost like a Rorschach test. You're going to be able to do this in your head. And I've been tempted every semester to just not do it. But it turns out that the message in this page is one of the most important messages before the next exam. The people that don't understand this page are going to have a hard time on the exam. Now, in this problem, we shoot an arrow into a haystack, and it travels 1 meter in 1/10 of a second and stops. Then we take a second arrow, actually it's the same arrow, but we fire it again, this time twice as fast. Now, let's be clear. Greg's a city boy. I was raised in a bunch of cities. We moved around a lot, but we always lived in the city. Those of you that grew up on a ranch or a farm know that the deeper you go into a haystack, the more it's going to resist the motion. But this is city hay, okay? This is city hay, and the friction force is going to be the same no matter how deep that arrow goes into the haystack. It's city hay, hay. Okay? So really quick, see if you can solve all of those questions. Think of it as a Rorschach. Seen it and it went really quick. If you haven't, you're still struggling. Let's work that together. Part A asks us, how much more kinetic energy does the fast arrow have than the slow arrow? Well, kinetic energy is 1/2 mv squared, which we can write as 1/2 mv times v. Now, if I shoot the same arrow the second time, then the mass is going to be the same. But it's going twice as fast, we're told. So this gets twice as big, and so does this. And that means that the kinetic energy gets 4 times as big, because the speed is squared. So my kinetic energy initial for the fast arrow is going to be 4 times the kinetic energy initial for the slow arrow. Now, on B, it asks us how much more momentum would the faster arrow have? Well, momentum is linearly related to velocity. Again, it's the same arrow, so the same mass, but the speed doubles, and so that means that the momentum doubles, and that means that the momentum initial for the fast arrow is twice as big as the momentum for the slow. Slow, spelled without an N. Now, here's the point of this page. When you get to that midterm, every problem's going to be either energy or momentum. But if you try to use momentum to solve an energy problem, you're going to get 0 points. There's just nothing we can do for you. If you try to use energy to solve a momentum problem, you're going to get 0 points. So in each problem, you've got to ask yourself, is this energy or is this momentum? And making the right decision is critical. Now, this page teaches you how to make that right decision. Part C here asks, how much time is required to stop the faster arrow? If we are looking for time, or if you're given time and expected to use it, is that energy or momentum? It's got to be momentum. You never learn anything about energy from time, or anything about time from energy. They're exclusive, okay? So anytime you're dealing with time, it's a momentum problem. So let's use the grand high impulse momentum equation. This is part C. The momentum initial is equal to the momentum final, except when it's not, when there's a force acting for a time. Now the initial momentum, we said, was the mass of the arrow times its initial velocity. And since this is a vector equation, we need a coordinate system. Let's call to the right positive and to the left negative. Since the arrow is traveling to the right, this would be positive momentum. Now when the arrow stops, the momentum is zero, because the velocity is zero. Now the force that is changing this momentum is the friction that is acting by the hay on the arrow. Now because that friction force is pushing on the arrow to the left, that would be a negative force. That would be the kinetic friction by the hay on the arrow, times the time. Now, the mass stays the same because it's the same arrow. The speed doubles. That means the positive part of this equation gets bigger by a factor of 2. In order for this to still be zero, the negative part of this equation must get bigger by a factor of 2. Because we're dealing with city hay, the friction force always stays the same. Doesn't matter how fast the arrow's going or how deep it is in the haystack. And that means that the time has to double. So that means that the time for the fast arrow is going to be twice the time for the slow arrow. The time for the slow arrow was 0.1 seconds, so this is going to be 0.2 seconds. D. How far does the faster arrow go? Now again, just like anytime you have time, it's a momentum problem. Anytime you have distance, it's going to be an energy problem. You never learn anything about distance using momentum. It's got to be energy. Force times distance is the verb that changes energy. So let's use energy. And in this problem, there's no springs. If the arrow is shot horizontally, we call that height 0. There's no gravitational energy. The only kind of energy we're talking about is kinetic. So initially I have 1/2 mv squared. I'm going to call it v times v. When the arrow stops, I have 0 kinetic energy. And those are different because there's negative verk done by the friction force. Now, why is that verk negative? It has nothing to do with the force being in the negative direction. Energy is a scalar, it's not a vector. The important thing is the force is acting one way and the arrow is going the opposite way. And it doesn't matter what those ways are, if they're opposite, that's negative verk. So I put negative force, the friction force, by the hay on the arrow times the distance. We play the same game. It's the same arrow, so the same mass. The speed doubles here and here. So that means the kinetic energy gets 4 times bigger. In order for this to stay 0, the negative part of the equation must also get 4 times bigger. Since the friction force stays the same, that means the distance has to get 4 times bigger, and the distance traveled for the fast arrow will be 4 times the distance for the slow. Since the slow went 1 meter, this would go 4 meters. Now the last part of this page asks, is that consistent? This arrow went 4 times as far in only twice the time. And the answer is yes, that's consistent. Let's say you and I are going on a road trip in different cars. I go 30 miles an hour because I'm old. You go 60 miles an hour because you're young. I only drive for 4 hours during the day because I'm old. You drive for twice that amount of time, 8 hours, because you're young. How much further down the road are you going to get than me? 4 times. Twice as far because you're going twice as fast, and twice as far because you're going twice as many hours. So yes, it's consistent.